This is the first lesson on sequences and series. We're going to learn to use something called subscript notation. We're going to generate a sequence using a rule, very similar to what you've done previously in GCSE. Generate a sequence using something called an inductive definition, and describe the behavior of various sequences. Two examples of different types of sequences. The first one's what we call a finite sequence. For these type of sequence, we've got a first and a last term, a finite number of terms. An infinite sequence, and you'll see this is a very familiar type of sequence, similar to a lot of the sequences you've met at GCSE. The sequence goes on forever, and you can see this sequence, each term's going up by 3, so it'll just continue doing so. So the notation we tend to use in AS level maths is this type of notation here, where rather than talking about nth terms and rules for nth terms, we use this, what we call an inductive definition, using subscript notation. So u with the subscript n equals 3n minus 5. We can use this to find the first term. We simply place a 1 in for the n, so we get 3 times 1 minus 5. Second term, 3 times 2 minus 5, and so on. And we can see there that we can work out now the value of those first 5 terms as minus 2, 1, 4, 7 and 10. Okay, have a go at these. Work out the first 6 terms, the 50th term and the 100th term, and have a little think about what's going on. Think what happens if the value of n gets bigger and bigger. Pause the presentation, have a go and have a think about it. Okay, well, some interesting ones here. This one here is very similar to the one we've just looked at. We're just multiplying the n by 3 each time and adding 2. So this one's going to keep going up by 3, starting at 5, isn't it? Quite simple for the 50th term, just 3 times 50 plus 2. And for the 100th term, 3 times 100 plus 2. This one here is quite similar. Instead of un, we've used cn there, but it really doesn't matter. It serves the same purpose. And here we're subtracting 4 times n, so it's going to keep getting smaller and it's going to keep going down by 4 with each subsequent term. We can see here we've got a quadratic. We're squaring the n here, so that's obviously going to give us quite big numbers when we get up to 50th and 100th terms. This minus 2 to the n is quite interesting. Hopefully what you notice there is with odd powers of n we get negative numbers, and with even powers we get positive numbers, and the sequence does something called oscillate either side of 0. And another very interesting one here, this t to the n sequence here, 2 plus 1, 3, 1 over 2 a half, 1 over a third, that gives us 2 and a third, 2 and a quarter, and so on. 2 plus 1 50th for the 50th term, 2 plus 1 100th for the 100th term. And as the n's getting bigger, hopefully you notice that this fraction's getting smaller and smaller, closer to 0, and the value of each subsequent term is getting closer to 2. So, if we've got this sequence here, write down the terms of the sequence. And that's what we get. We put 1 in for the n first, 3, 8, 13, 18. Another way of thinking of this is how we get from one term to the next term. So if we know that each term's going up by 5, we could say that the second term is the first term plus 5, or the third term is the second term plus 5, or the fourth term is the third term plus 5, etc. In general terms, we could write un plus 1, the n plus 1th term, is equal to un, the nth term, plus 5. So the next term is the current term plus 5. This type of relationship, this type of way of writing sequences in terms of how we get from one term to the next term is called a recurrence relation. And in this particular one, you can see that this plus 5 is the recurring element, isn't it? To get to each next term, we're always adding 5. Okay, so if we define our sequence like this, with this recurrence relation, can we write out the terms? Well, we could write out some terms that obey this rule, obey this recurrence relation, but there's something missing. And the extra information, hopefully you've thought of it for yourselves, the extra information you need is a term to work off, usually the first term, but in fact any term would be sufficient information if we knew which term it was for us to be able to derive the separate terms of the sequence. So you need to know a term, and it's usually the first term we're given. So given this recurrence relation and the fact the first term's 7, we can now write out the sequence. u1 equals 7, u2 equals 4, u3 equals 1. We just simply put the first term in there, 7 minus 3 gives us a second term. It's then 4 minus 3, which is 1, to give us the third term. It's then 1 minus 3 minus 2 to give us the fourth term. Minus 2 minus 3 gives us minus 5, and so on. Okay, a problem for you to try. If you can do this, then you're perfectly ready for the lesson on this. If you can't do this, then perhaps go over and reinforce what you've learnt in the video so that you'll be ready for the lesson. So we're looking to find k. Pause the presentation and have a go. Okay, to find k, we'll write down what we know. We know that u1 is 3. We know that to get to the next term, we add k to the previous term. So the second term is 3 plus k. The third term will be 3 plus k plus another k. In other words, 3 plus 2k. And to get to the fourth term, which we know the value of, we would add k again to this. So we get 3 plus 2k plus k, in other words, 3 plus 3k. And we know that that has a value of 7.5. If we subtract the 3 from 7.5, we get 4.5. And if 3k is 4.5, then clearly k is 1.5.